All right, so welcome to this series of Calculus 2 videos where I will be preparing you students who are taking Calculus 2 sometime maybe in the fall, winter, or maybe even the summer. So hopefully these series of videos will be able to help you go over uh, what you really just need to know about Calculus 2. For example, later on we'll be talking about integration. We'll also be talking a little bit about techniques of integration and so on. But I'm also going to be adding a little bit of complex numbers as well, just so that we could be at least familiar with the concept of complex numbers, which will appear in maybe in some of your courses as well. So that's why I want to briefly go over them. So anyways, let's get started for today. So for first, we're going to be having a review session about Calculus 1, mainly just on like the derivatives and some important stuff that we could be having a look at. So the first topic that we'll be having a look at is the derivatives of trigonometric functions. So we have two limits that are important for proving the derivatives of trigonometric functions. So we have for the first one that the limit as theta approaches 0 of sine theta over theta is equal to 1, as well as the other limit where we have the limit as theta approaches 0, cos theta minus 1 divided by theta is 0. So we can determine the derivative of sine of x by using the definition of the derivative. So let's have a look at this. All right, so recall that the definition of the limit is given by, so f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x. All this is divided by h. And now since here our f of x is going to be the sine of x, so the first one will have sine of x plus h. So we have the limit as h approaches 0 of sine of x plus h. And minus f of x, which is just going to be your sine of x. And all of this is just going to be divided by h. So remember that the double compound angle formula, so recall here that if you have sine A plus B, that this is also the same as sine A cos B plus cos A sine B. Now using that here, we could say that, well, if we split the limits together, or split the limits apart, so we would have sine x, sine of h, or cos of h, plus cos of x times sine of h. And we have minus sine of x. And all of this is divided by h. So here, we could see that, well, we could actually common factor out a couple of terms here. We could common factor out the sine x and this sine x here. So let's go ahead and common factor that out. And I'm also going to keep this cosines together and part of the sines together. So let's see. So we have, by common factoring out the sine, so we have the limit as h approaches 0 of the sine of x. And so that means we'll have a cos of h minus 1. And we'll also have a cos x sine of h. All of this is divided by h. Now I'm actually going to rewrite the denominator a little. So if I break up the denominator a little, so say I break this part divided by h, this part I also divided by h as well. So now what we see here, if we take the limit of h approaches 0, if we see this part here, this part is going to go to 0 because according to our limit here, it's going to approach to 0. So we know that if we take the limit of this part, is actually just going to go to 0. And similarly, since we know that the limit of sine theta over theta as theta approaches 0 is equal to 1, so that means this part over here is also going to approach 1. So sine h divided by h is going to be 1. And so that means what we're left with, so after we compute the limit, we're just going to be left with the cosine of x here. So that means the derivative of sine is cosine of x. Now, similarly, we could also determine that the derivative of cosine of x is simply negative sine of x. But while we're using these definitions, we could also find the derivative of other trigonometric functions. For example, the next example, we'll be having a look at finding the derivative of tan of x. But we're going to use the standard way using the quotient rule for this derivative. So if we want to find the derivative of tan, well, recall that the tan here is also the same as saying sine x divided by cos of x, right? So that means we're going to take the derivative using the quotient rule. So if you remember the quotient rule here, so quotient rule, if you want to take the derivative of f divided by g, you have to take the derivative of f multiplied by g minus f multiplied by g prime, all this divided by g squared. So here our f is going to be our sine and our g is going to be the cosine. So if we take the derivative of this, so we say f prime of x is equal to, so the derivative of sine is going to be cosine of x multiplied by the cosine of x and subtract the sine of x. And we also multiply by negative sine of x, which is the derivative of cosine. All of this is divided by cos squared of x, right? Now we could see here, if we simplify the numerator a little, so this is part over here is going to be positive sine squared of x. This is going to be cos squared of x. So we have that. So this top part, we have cos squared of x. And this entire part is going to be plus sine squared of x. Now this is by Pythagorean's identity, which means that it's going to be equal to 1. So we have 1 divided by cos squared of x. And therefore, this is equal to secant of squared of x, which you could also see down here that is also equal to secant squared of x. But so that's the derivative of tan of x, right? So let's have a look at the next example or next bit of examples. So the next set of examples is just working with the product rule, with the quotient rule, and the chain rule as well. So let's have a look at these ones. So differentiate the following functions. So for the first one, part A, we have f of x is equal to x times sine of x. So this is going to be using the product rule here. So recall the product rule is given by, so if you have fg, if you're multiplying two functions together, you have f prime g plus fg prime. So that's the derivative of two products or two functions here. So if our f is going to be our x and our g is going to be our sine of x, then that means the derivative f prime of x is simply just going to be, so we have the derivative of x, which is 1, multiplied by sine of x, and x multiplied the derivative of sine, which is cosine of x. And if you want to simplify things, it's just going to be sine x plus x cosine of x. And that's all for this one. Now for part B, let's have a look at this one. So we have y is equal to secant of x divided by 1 plus secant of x. So if we go back to the derivative here, we note that the derivative of secant of x is equal to secant of x times tan of x. So let's go ahead and use that. So what we have here, so we're going to say that, well, dy over dx, then, so we're going to use the quotient rule once again. So we're going to take the derivative of the numerator first, which is secant of x tan of x. So secant x tan of x. And you multiply by the denominator function. And you subtract it by secant of x. And you multiply by the derivative of the denominator, which is just going to be secant of x tan of x though. Or I'll just leave it without the bracket. Tan of x. And all of this now is divided by 1 plus secant of x squared. Okay, so let's expand the first term. So we get, we have a secant x tan of x. And we have a secant squared of x tan of x. And we're also going to subtract it by secant squared of x tan of x. So here we see that, well, the secant squared of x tan of x will cancel out with this. And we're still going to be dividing this entire thing by 1 plus secant of x squared. And what that leaves us is with secant of x tan of x all divided by 1 plus secant of x squared. And that's the derivative of secant of x plus divided by 1 plus secant of x. Okay, so the third part here, part C, we have the function y that is in terms of u. So that means y here is equal to y in terms of u. So that means the c here is actually our constant number. So once again, we're going to be using our product rule once again. So we're going to take the derivative of y. So we have dy divided by dx. So this is equal to the first term. So that's e to the power of u multiplied by cos of u plus c times u. And we're also going to add, so e to the power of u and the derivative of cos x, which is negative sine u, and plus c. Now I could clean things up a little by common factoring out the e to the power of u on the outside. So I'm going to take the e to the power of u so that we have cos u plus cu minus sine u and plus c. And that would be the final answer, but you could either keep it one or the other, but I think this one would be a bit easier to work with. All right, so that's part C. Part D over here, we have another function where uses the chain rule this time. So we see here that if the function is in terms of x, then this a to the power of 3 is actually our constant term. So that means we're going to have to treat it as a constant. So everything we're going to take the derivative of is going to be with respect to x. So dy over dx here. We then have, so the derivative of cosine is negative sine. So you have negative sine a cubed plus x cubed. Now we also take the derivative of the inner function. So since this is a constant, this is going to go to 0. Then the derivative of this is going to just be 3x squared. So we would just have to multiply by 3x squared. Or if you want to simplify things, this is 3x squared sine a cubed plus x cubed. And that's all for this part. And as for the last part, now, although this might look a bit tricky, I promise it won't look as bad or be as bad. So what I'm gonna do, so this is chain after chain after chain. So that's what we're gonna have to do. So the first step is that we're gonna actually have to take the derivative of the outside function. So we're taking the derivative of this part here. So the derivative of the sign that's on the first line, so that's talking about this one here, is actually just going to be cos and whatever's on the inside. Sine of x cubed. 1. And now we're going to multiply by the inner part. So we're going to take the derivative of this part next. So from this sign, we're going to, once again, put it as a cosine of sine of x cubed. And then same thing, we're going to take the derivative of this sine of x here, sine of x cubed, so that we get cos of x cubed. And lastly, we take the derivative of the x cubed, which is just going to be 3 times x squared. So what we could rewrite then, could simplify things. So you have 3x squared cos sine x cubed cos sine x cubed and cos x cubed. So that's all for this example. And those are the 5 parts of the derivatives that we are going to be having a look at. So let's move on to the next topic here. Okay, so we're also going to be having a look at inverse trigonometric functions. So we also have to recall what implicit differentiation is. So what that means is we're going to take a derivative of a function that is sometimes with respect to x as well. So whenever we have y and x on the same line, for example, then that means we're going to have to probably use the product rule and maybe have a derivative on the front. So for example, let's say if we differentiate x times y is equal to 1, well, if you want to use the product rule here, then we would just have y plus x times dy over dx, which is equal to 0. And then you solve for x here, or solve for dy over dx. So that would just be negative y, so dy over dx would then just be negative y over x. So that would be the implicit differentiation that we're actually going to be working with now. So let's have a look at the inverse trigonometric function of sine of x, sine inverse of x. So we want to differentiate this function. Well, first of all, let me rewrite this as y, or x, is equal to sine of y. Now, noting that y is actually a function of x, when we take the derivative on both sides, so I'm going to take with respect to x, so d over dx of x, that is equal to d over dx of sine of y, but y is a function of x, so I'm going to write it as y of x. So when we take the derivative, the left-hand side just becomes 1. The right-hand side becomes cosine of y, but we also multiply it by y prime, or dy over dx. So let me put it this as dy over dx. Then since we want to solve for dy over dx, so we bring the cosine to the other side. So we have dy over dx, which is equal to 1 divided by cosine of y. But what is cosine of y? So let's go back to the original function y is equal to sine inverse of x. So whenever we're trying to find an angle, so y here is actually going to be this angle. So if we draw a right angle triangle here, so that means we have the right angle here. Then that means this is going to be y. This is our angle y. Then, so since sine, remembering that it's opposite over hypotenuse, so our opposite is going to be this x, so this opposite. This is hypotenuse. So that means we have a 1 here and we have x here. So that means if we want to find cosine, we are going to have to know what this length is. So by Pythagorean theorem, we could automatically know that this is 1 minus x squared, all of that square root. Now, cosine of y, we could actually find what that is based on the right angle triangle that we have constructed. So remembering that cosine is adjacent over hypotenuse, so we could say that cos of y is just going to be the root of 1 minus x squared divided by 1. So it's just going to be at the bottom. So therefore, the derivative of sine inverse of x is just going to be 1 minus x squared. And that's the derivative of sine inverse of x. So analogous, we could also find the other inverse trigonometric functions using the same ideas that we have used above, most likely by implicit differentiation and so on. So let's try to differentiate the following functions. So for the first one, we have y is equal to sine inverse of 2x plus 1. So using the derivative of sine inverse of x, so this is this part over here, where in place of x, we're actually going to be using 2x plus 1. So this is also going to be using the chain rule. So what we say is that, well, dy over dx is equal to 1 divided by root 1 plus 2x plus 1 squared. All of this, and then we also have to multiply by the derivative of 2x plus 1, which is just equal to 2. And so therefore, the entire derivative is just going to be 2 divided by 1 plus 2x plus 1 squared. So that's for the first part. Now for the second part now, we do something similar, but we're using the cosine definition. So in place of the x, we're going to be using e to the power 2 times theta. So what that means, so if we say f prime of theta, we say that, well, the derivative of cosine inverse is 1 divided by root 1 minus. Now what goes inside is actually e to theta, whole thing squared, and the derivative of the inner function, which is 2e to theta. So simplifying things a little, what we get is 2e to theta still, but all this is divided by root 1 minus e to the power 4 theta. And that's all you would have to do for this part. All right, so that's mainly about the inverse trigonometric function. So let's move on here. So now let's have a look at the hyperbolic functions here. So first of all, let's start with the exponential functions, e to the power of x and e to the power negative sine of x. So for e to the power of x, remembering that e to the power of x is an increasing function and an exponential function, so it's going to look something like this. And similarly, since e to the power negative x is a decreasing function, the function is going to look something like this then. All right, so those are our two functions. We have y is e to the power of x, and this is y e negative x. All right, so now let's have a look at the two hyperbolic functions that we're going to be exploring here. So the first one is actually the cosh. So we say y is equal to cosh of x, which is actually similar to the function, or which is actually supposed to be equal to the function. So we have cosh of x that is equal to e to the power of x plus e to the power of minus x divided by 2. And how this would look like? Well, if we were to use the superposition principle to add the two functions together, we see that, well, if we add majority on this side and then majority on this side, we think it's going to look somewhat like a parabola. So obviously it's going to have some form over here and another form on that side. So that's what the hyperbolic function of hyperbolic cosine is going to look like. So similarly, for sinh of x, we define it similarly, but using exponential functions. So instead of adding the two exponentials and then dividing it, we're going to be subtracting it and then dividing the whole thing by 2. So that means sinh of x is actually equal to e to the power of x minus e to the power of minus x, all this divided by 2. So what this would look like then is somewhat like this. Now, although this looks like a cubic function, it's not quite exactly a cubic function here. So these are the two hyperbolic functions that we will be working with for the next bit. All right. So once we get to this part, so we're going to ask ourselves this question. So why are they called the hyperbolic trigonometric functions? So remember that the definitions of the sine and the cosine, they actually define a unit circle when we use them as the x and y coordinates. So for example, if I draw a circle, I'll try my best to draw a circle. So it looks something like this. Let me move this a little. So it'd be over maybe here. All right, that's fine. So if that's our unit circle, so that means each of the arms here, if we draw an arm with radius 1, we see that this point on the circle is actually our cosine and sine functions. So this is actually given by the cosine of x, comma, sine of x. So this means that the distance between here to here, so this length here is actually our sine of x. And the distance between here to here is actually going to be our cosine of x. And the unit circle carries values from -1 to 1 on both the x and y axes here. So that defines the unit circle. So that means, if remember by Pythagorean's identity, we know that cos squared of x plus sine squared of x is equal to 1. All right. So whenever we consider the hyperbolic functions instead, well, now that's actually going to be a little bit different, because we're actually going to be ending up having two types of asymptotes. So one asymptote would actually be coming from this line, and the other line would be coming from this side here. So it looks something like that. Let me fix the line. So it looks something like that. So we have those two asymptotes, and we have a point here and another point here that would actually be extending to this side and to this side. And the other side we have from this side and this side as well. So that's what it would look like using cosh and sinh of x as the coordinates. So we have cosh of x and sinh of x. And as a matter of fact, we could actually note that cosh squared of x minus sinh of x, or sinh squared of x, is equal to 1. So the point that we would pick here, so take any point. So say this is going to be your sinh of x, and this is going to be your cos of x, right? And that's the result that we would take. So let's have a look at the next example. So let's say we want to determine the derivatives of sinh of x and cos of x. Well, let's have a look at the derivative of cos of x first. So the derivative of cos of x. So remember that cos of x here was actually given by, so dy over dx, or sorry, it should just be d over dx of e to the power of x plus e to the power of minus x, all this divided by 2. Now, so that means we actually had to take the derivative of each of the e to the power of x's. So we could also take the constant 1/2 on the outside, take the derivative on the numerator. So derivative of e to the power of x, which is just going to be e to the power of x itself. Take the derivative of e to the power of minus x, that's going to be negative e to the power of minus x. So what that actually equals to e to the power of x minus e to the power of minus x divided by 2. So we see here, remembering that the formula for sinh of x is actually what we have here. So that's equal to sinh of x, sinh of x. So that means the derivative of cos of x is actually the same as sinh of x. So let's take the derivative of sinh of x now. So we have d over dx of sinh of x is equal to d over dx of the same thing. So e to the power of x minus e to the power of minus x. All this is divided by 2, right? Now we take the derivative again, so that would be e to the power of x plus e to the power of minus x, all of this divided by 2. See, this now is actually equal to cosine, cos of x. So those are the two derivatives. So we see that the derivative of sinh of x is cos of x. The derivative of cos of x is sinh of x here. All right, so that's good. So let's see for the next part. So this page here actually just gives you a list of the hyperbolic functions, hyperbolic identities, derivatives of hyperbolic functions, inverse hyperbolic functions, then the derivatives of hyperbolic functions. So this is just basically a summary of the identities that you should be aware of. But other than that, let's move on to the next session that talks about the L'Hopital's rule. It's a very short section for this one. So whenever we're talking about L'Hopital's rule, we want to make sure if we have two functions, so say that f and g, so say f and g are two functions such that if you take the limit as x approaches 0, for example, of f of x divided by g of x, and you get a 0 over 0 result. This does not mean that the limit does not exist. So this does not mean that the limit does not exist. The thing is, if you get an indeterminate form 0 over 0, take the derivative of both f and g. Then, so you would have limit as x approaches 0 of f prime of x divided by g of x. This could give you some number, let's say that's equal to L. So it's easier sometimes to work with L'Hopital's rule, or sometimes you could also use techniques, for example, factoring, rationalizing, etc., to actually obtain this value L. So that's the purpose of L'Hopital's rule, and we'll have a look at some examples. However, one thing to note here, whenever you have a number, so number on the top, divided by 0, then that's when the limit does not exist. All right, so it only can happen when you have an indeterminate form. So you could also have infinity over infinity as well. That would also be an indeterminate form. Okay, so let's have a look at this example. So the first example we have is the limit as e to the power of x minus 1 divided by x. So see that when we plug in 0 into, if we do a direct substitution into the formula, we obtain that, well, e to the power of 0 minus 1 divided by 0, which is 1 minus 1 divided by 0, which is 0 divided by 0. So we get an indeterminate form. So this is indeterminate. So what we actually need to do here is take the derivative of both the numerator and the denominator. So what I'm going to do is put the L and the H in front to denote that I'm using L'Hopital's rule for this step. So we have that the limit as x approaches 0. So the derivative of the numerator is just going to be e to the power of x. Divide this by the derivative of the denominator, which is x, which is going to equal to 1. So that means you're actually going to be taking the limit as x approaches 0 of e to the power of x. And if you put in 0 in, so e to the power of 0, this is equal to 1. Not too bad. So it's also important to note that the limit here, as x approaches to some number of f of x divided by g of x, if you get an indeterminate form of this case, then this would also be the same as the limit as x approaches a of f prime of x divided by g prime of x. So that's because they're not necessarily going to be, so if you get a 0 over 0 in this form, but not a 0 over 0 form on this side, then this is the one that you're actually going to be having to take. All right. So let's have a look at this example. There's a typo here, so this should actually be an x here. So let's take the limit of this. So we had the limit as x approaches 0 of 1 minus cos of x divided by x squared. So see here that when we do a direct substitution, we have 1 minus cos of 0 divided by 0 squared, but cos of 0 is 1, so 1 minus 1 would be 0 over 0. So we have a 0 over 0 form, so meaning that we actually need to use L'Hopital's rule. So using L'Hopital's rule, so equal sign with the LH on the top, then we would say that we have the limit as x approaches 0. So the derivative of the numerator here is going to be sine of x, because negative derivative of negative cos of x is sine of x here. So we have sine of x divided by 2 times x. However, if we put in 0 over 0 again, we get another indeterminate form because sine of 0, which is 0, and 2 of x, it's going to be 0 as well. So that means we're actually going to be using L'Hopital's rule one more time. So one more time, we say that, well, the derivative of sine of x is going to be cosine of x, and we divide it by the derivative of 2 times x, which is just 2. And I'm forgetting the limit on the outside. This is the limit as x approaches 0. So if we now do this direct substitution, cosine of 0, which is 1, and we just get 1/2 as a result. So that's the L'Hopital's rule. And so let's move on to the next session where we have a look at 2 important theorems in this case. So for the first theorem, we're going to be having a look at Rolle's theorem, which states the following. So if f is a function that is continuous on a closed interval a times b, a to b, and f is differentiable on the open interval a to b. And one more thing, if fa is equal to f of b, then we say that there exists a number c that is somewhere between a and b, where the critical point f prime of c is equal to 0. So there has to be some point between a to b where the graph is horizontal. So that's what the last sentence is saying here. So we say that there exists a point where the function or the graph is horizontal. So that is Rolle's theorem. So if we try to visualize this a little on a graph, for example, so say we have our axis here. Let me try to make this a bit more horizontal. So we have, say we have a function that looks something like this, a to b. So here is going to be a, this is b. And say we, for another graph, let's say that we have this graph that looks something like this, where we have this point being a, and we have f. This is going to be b. So between this, so this is going to be a continuous function. So that means no removable discontinuities, no jumps, and so on. And it's also differentiable in everywhere on this line, except maybe their endpoints. So so we say that there is a number c. So this is going to be the point c here, where the f prime at c is actually going to be equal to 0, meaning that you're actually going to get a horizontal tangent line that passes through this line here, or this point. And same thing on the other graph as well. So you have a point here where this is going to be called point C. And this line is where the where the graph, or where the tangent line is actually horizontal. So that's Rolle's theorem. So that's nothing too bad. So let's have a look at the next theorem, which talks about the mean value theorem, which is very useful in a lot of applications. So let's say that f is a function that is continuous on AB, on the closed interval AB. F is also differentiable on the open interval AB. So we say that there is a number c. So once again, we also have a similar conclusion where the derivative of c, derivative of f evaluated at c, is also the same as the slope of the secant line from A to B. So on the right-hand side, we have the slope of the secant, and the left-hand side, we have the slope of the tangent. So what that means, so visually, if you have a graph that looks like this, and so let's say we have a curve that goes somewhat like this from A to B. So here's B, and here's A. So let's say we have a tangent from A to B. So the slope of the secant from A to B. So here's point A, here's point B. So this is BFB, and this is AFA. So this secant line going from A to B actually has the same slope as a critical point that could exist, or that exists maybe just slightly below the line here. So maybe somewhere here is where the function will have the same slope as the secant line here. So let me change the color of this one to maybe green. So this line over here, this is the point C, where f prime of C, so this is the derivative slope of tangent at point C, is actually the same as the slope of the secant line. So we say that So we say there is a point on the graph that has the same slope as the line from A to B. So that's what the mean value theorem is saying. Okay, so that's all for the two theorems that we're going to be having a look at. And the next section, we'll be having a look at the antiderivatives. Okay, so let's say we have a function, because we know that the derivative of a position function is going to be the velocity function, and the derivative of the velocity is the acceleration. But let's say we want to know, if we know the velocity, what is the position? So for example, let's say we have the function that is given by vt is equal to t squared. So that's the velocity function. But we know that the velocity is the derivative of the position. So let's try to work backwards to determine the position of the object by thinking about the power. Okay, so our goal is to find out what v s of t is, which is the position function. Well, we know that s prime of t is also the same as vt, which is equal to t squared, right? So if we go backwards one step, we know that, so if we start with derivative, so we start with t cubed, and we also going to be multiple, but we know the derivative of this function is going to be 3t squared. So we have some common similarities between this one and this one here. But what we just want is just the antiderivative for vt. So instead here, in order to get a derivative of this function, just the t squared here, we're actually just going to be dividing by 3 instead. So that means the position function s of t is just going to be a third times t cubed. And, well, the next part here says that, well, is this the only function that works? The answer is no. Because you could also have a position function, s of t, that is 5 units above where it's actually starting. Or you could also have another position that starts maybe like 100 units below where it's actually supposed to start. So you could actually have multiple types of constants at the end of the antiderivative. So in general, the general antiderivative of a function f on the interval I is actually f of x plus c, where c is actually just the arbitrary constant of f of a particular antiderivative f on the interval I. Okay, so let's have a look at the following functions. So we want to determine the antiderivative of cosine of x. Well, we know that the derivative of cosine of x, or derivative of cosine of x, so let's have a look here. Well, if we have the derivative of sine of x, take the derivative of this, we know that is equal to cosine of x, right? So that means if we take the antiderivative, so the reverse derivative of cosine of x, we should actually just get the sine of x here. So that means f of x would actually just be sine of x plus c. Now, b is also is a function that you might not really see that often, but if you remember, so if we take the derivative of ln of x. So this is the natural logarithm of x. This is actually just equal to 1 over x. So the antiderivative here, so if this is the derivative, and if we want the antiderivative, so we would take this as our function f of x, take the antiderivative, we should get natural log of x. So that means f of x here, or big F, is going to be ln of x plus c. And same thing for the other ones, the derivative of e to the power x, which is just going to be e to the power of x. Take the antiderivative of it, so we would just get f of x is e to the power of x plus c. Now, this one is actually one of the trigonometric functions that we had a look earlier. So remember that d over dx of tan inverse of x is equal to 1 divided by 1 plus x squared. So that is actually just going to be our antiderivative. So f of x is tan inverse of x plus c. Okay, so let's try to complete the table. So whenever we have a function, let's say we have a constant function, so f of x is equal to a, then the particular antiderivative here would simply just be the constant itself, so f of x would just be the constant x, a times x. That is the antiderivative. Now say we have the function f of x is x to the power of n. This antiderivative, well, if we work backwards, so we're going to have to add 1 then. So we have the x to the power n plus 1, the derivative of that. Usually the derivative would be n plus 1 times x to the power n minus 1, or n plus n, yep. So that means instead of that, we would actually have to divide it by n plus 1 here. That's the antiderivative for x to the power of n, and other functions including sine of x. You could conclude that this is going to be negative cos of x. We could also say cos of x, that this antiderivative is going to be sine of x, and 1 divided by x is going to be natural log of x, and e to the power of x, which is just e to the power of x, which are the ones that we have saw a little bit up here as well. So it was pretty much just a copy and paste onto this table here. Okay, so in some instances, we're given additional information about the function that where we actually want to determine the constant value. So once again, say we have vt is t squared, which is the velocity. If it is known that the object is at a position of 10 units at t equals to 3, let's try to determine an exact expression for the position. So if s of t here, we found that it was going to be 1 over 3 times t cubed plus c. But we're also given that s of 3 is equal to 10. So by substituting those values in, you have 10 is equal to 1 over 3 times 3 to the power 3 plus c. So we get 10 is equal to 9 plus c, and so c is equal to 1. So what that means, the exact expression for this type of situation is just going to be 1 over 3 t cubed plus 1. Okay, so let's try to do the same with the next few examples as well. So let's say we want to find the antiderivative of the given information, f, and we're also given the information that maybe f0 is equal to 4. So using the table that we have up here, we could always find the antiderivative with no problem now. So for the first one, we have f of x is equal to 5x to the power 4 minus 2x to the power 5. Well, if we take the antiderivative of this, and using the table that was on the previous page, we see that f of x here is x to the power 5 for the first term, and minus 1 over 3 x to the power 6 from the previous page as well. And we'll also have a plus c out here, which is a constant. So now we're given that f of 0 is equal to 4. So when we substitute f0 is equal to 4, then we would have that 4 is equal to 0 to the power 5 minus 0 to the power 6 and plus c. So that means c is equal to 4, right? And so when we put it back in, so that means our exact antiderivative is x to the power 5, 1 over 3, x to the power 6 plus 4. And that's the exact expression. And so let's have a look at part B, where we have f of x is equal to 4 times 3 times 1 plus x to the power x squared to the power negative 1. We're given that f at 1 is 0. So we could also rewrite this a little. So note that this part here is also the same as saying, so we have 3 divided by 1 plus x squared. We know the antiderivative of this. We found it over in part D here. So if we put it in, so we know the antiderivative. So f of x here would just be, well, 4 times x, which is a constant, minus 3 tan inverse of x plus c. It's because we're going backwards on the derivative. So now given that f1 is equal to 0, we could put that in. So we have 0 on this side. We have 4 minus times 1. And so that's 3 times tan inverse of 1 plus c. Well, tan inverse of 1 is just going to be pi over 4. So that means 0 is 4 minus 3 pi over 4 then, plus c. So that means c here is 3 pi over 4 minus 4. So that means f of x here, the exact expression, is 4x minus 3 tan inverse of x plus 3 pi over 4 minus 4. And that's the expression. And on to the last section, where we'll actually be talking about the series and summations. Okay, so sometimes it's convenient to write expressions using, if you have a series of terms, it's usually convenient to write it as a summation notation, using the summation notation. All right, so let's have a look at a quick example. So say we have the sum from k is equal to 3 to 12 of 2 times k squared. So we're always going to increase by 1, starting from 3, until you reach k is equal to 12. So what that means, we're going to start from 3 squared, right? And we're going to keep on increasing this. So 2 to the power 4 squared plus 2 to the power 5. 2 times 5 squared plus 2 times 6 squared plus 2 times 7 squared. And you could keep on adding this until you reach 2 to the power, or 2 times 12 squared, which is some number. You could probably calculate that on your own, but that's okay for this part. But that's just the idea of the summation that we want to get used to. So there are some rules for the summation notation here. So the first property is that whenever you have a constant c here, multiplied by the series of numbers but given by xk, this is just going to be c times the sum of xk. So we're just simply bringing the constant multiplier on the outside. And same thing, or similarly for the second property, we could always expand the summations into each of the individual sums, so that we just have the sum of x plus or minus the sum of y. Now, this one's going to use a little bit of a pattern here. So whenever you're going from A to C, then you're going to go from C plus 1, so the next term after C, to B. Then if you combine these, you could actually combine these two so that you could actually have a sum from A to B instead. So for example, let's say you go from, take the sum from K is equal to 2 to maybe 8. So K squared, for example. Say you add that by K equal to 9 to 20, let's say, of K squared. So that means you're going to take everything from 2 to 8 using the same expression here, K squared, and then you're adding another set of terms from 9 to 20. Well, that's going to go from 2 to 9, or 2 to 8, to 9 to 20, or you could just say from 2 to 20. So that's also actually the same as saying the sum from K is equal to 2 to 20 of K squared. All right, so with these three properties, well, let's have a look at some expressions here. So let's say we want to determine the expressions for the following sums. So for the first one, we're going to go from 1 to n. So for example, this is actually just going to be 1 plus 2 plus 3 plus so on until you get to plus n. However, there's actually a direct formula for this. So one way we could actually do this, or one way that you would actually know about, is that this formula is actually just going to be given by n times n plus 1. All of this is divided by 2. So that's the formula for the sum of all natural numbers. Now for this formula for the sum of squares here, we have 1 squared plus 2 squared plus 3 squared plus dot 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 to n squared. So this formula here is actually just going to be given by the sum from k equal to 1 to n of k squared is actually just going to be n times n plus 1 times 2n plus 1 divided by 6. And for the case of when you have k cubed, so that means the sum of all cubes. So we have 1 cube plus 2 cube plus 3 cube plus dot 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 until you reach n cube. So this formula, you actually have the sum from k equal to 1 to n of k cubed. This is actually just going to be equal to n times n plus 1 divided by 2, but squared. And as for the last one, this is just going to be, so since c is just going to be a number here and does not involve k at all, you're just going to be adding a bunch of c's for n times here. So this part here is going to be adding c's for n times, right? So that means if you're going to add c's for n times, then that means the sum here from k equal to 1 to c is simply just going to be n times the c here. And that is all. All right, so that is actually going to wrap things up for this chapter here, or for this lesson here. The next lesson, we're going to be going on to talk about the complex numbers. So if you have any questions, just feel free to let me know in the comments down below, and I'll see you guys in the next video.